Okay, we stop at the young double slit experiment on page 18 of your lecture notes, so we will continue from there. So as mentioned, the light will pass through the light source. We need this. The light will pass through the source slit. We need this source slit S to ensure that the light will be coherent when it reaches S1 and S2. Then it spread, and in the straight through position at O, which is the same distance from S1 to O and S2 to O, you have the central bright fringe. This is also called the zero order maximum because the path difference is zero. Then we have the first order minimum, first order maximum, and so far so on. So now we're going to derive the equation that allow us to find the distance between the bright fringes. We say from the zero order to the first order, or zero order to second order. The distance between the bright fringes will be the same as the distance between the dark fringes. So the center of the dark fringe will be where we measure from center to center. Okay, so to derive that formula, firstly let's take a look at two waves coming from S1 and S2. So I have one light wave coming from S1, and then it hit on the screen at a point P. P is the nth order bright fringe. It could be first order, then n equals to 1, or second order, n equals to 2. So we are doing a general discussion here, nth order. Then the wave from S2 will also reach the point P. So these two waves, according to principle of superposition, they will superimpose and produce a resultant wave. So since P, right, is a bright fringe, so it must be constructive interference at the point P. If we look at the wave from S1 to P and from S2 to P, make a comparison, you can see that S2, right, is further than S1. Therefore, the path taken by the wave from S2 to P is longer than the path from S1 to P. We assume that the two rays are almost parallel because the distance from the two slits to the screen is large. Okay, compared to the small d, which is the distance between the two slits. So to find the difference in the distance between the two waves, I drop a line from S1 perpendicularly down from at 90 degrees to S2. Then S1P and AP, they will be of the same length. Then I'm going to consider this triangle, which is S1, S2, and the point A. I know that S2P minus S1P must be equal to n lambda, because at P it is a constructive interference, so the path difference between the two waves must be n lambda. Then looking at the triangle S2, S1A, I know that sine theta, okay, I label this angle theta here, so the sine theta will be equal to opposite, which is S2A. S2A is a path difference, which is n lambda, and divide by adjacent, divide by hypotenuse, which is d. So sine theta equals to n lambda over d. Then we're going to consider another triangle. This triangle here is PBO. In P is a spot where you have the nth order bright fringe. B is the distance that is a point that is in the middle of S1 and 2. And then O is the point on the screen that is the same distance from S1 and S2. Then this angle, right? Angle PBO is approximately theta. These two angles are approximately the same because the angles are small. So if I use tangent theta, I will have yn, which is the distance from the central bright fringe to the end of the bright fringe. Yn over d, big D, will be equal to tangent theta. Okay, since the angle is very small, using small angle approximation, sine theta will be approximately equal to tangent theta, and therefore I will have this equation simplified, make yn the subject. Yn, which is the distance from the central maximum to the nth order maximum, it will be given by n lambda big D over small, where n is the order of bright fringe, lambda is the wavelength of the light used, big D is the distance from the two slits to the screen, small d is the distance between the two slits. Okay, the condition for this equation to hold, right, is that the two angles must be approximately the same, and these two angles have to be small. So in order for this to be true, the D, right, the distance from the two slits to the screen, the big D here, have to be big, compared to the distance between the two sources. So your big D usually is in the range of about a few meters, 1 meter, 2 meters. Then your small d is a fraction of an mm. Past year A-level exam question asked before to state a value, suitable value for small d. So anything in the range of fraction of an mm, 0.1 mm to 0.9 mm is okay. So we need this in order to ensure that the rays are almost parallel from S1 to S2. That can be small. If I want to find delta y will be the distance from the n plus 1 order bright fringe to the n order bright fringe. Okay, so if I use n equals to 1, here will be y2 minus y1. So typically it's the distance between successive bright fringes. So to find delta y, I just need to make use of this formula. Okay. So yn plus 1, I sub in n equals to n plus 1. Yn is the same formula, but I use n is just n. So simplify, I'll have lambda big D over small d. You see that this equation, right, will be the same if I were to use this Yn equation and sub n equals to 1. So the delta y will be just 1 lambda d over d. Okay, in this animation here, you can see that the distance between the slits right here is changing. So this will affect the distance between the center and the end of the bright fringe. This is the middle one. So end of the bright fringe, you can see together get the second one. So when d is increasing, the distance actually decreases. Or you can look at the distance between successive fringes. So if you were to focus on, say, the center and the first order, when the d becomes smaller, fringe separation actually increases. So that is the inverse relationship. Now let's take a look at work example 5. Young double slit experiment. You have a two-slit interference experiment. It's used to determine the unknown wavelength of a laser source, as shown in the diagram below. Okay, so there's a laser source coming in. This is the slit. Actually, for a laser source, optional to have a single slit. So you can still have. So you have pass it through the single slit, then there's a double slit, and then you have to then get the interference pattern. Notice that the orientation of the slits is horizontal, so the spreading will be horizontal. Sorry, the spreading will be vertical, okay, because it's spread across as seen in the diagram, so the spreading is vertical. So you have the fringes here. So this is the straight through, which is the zero order maximum. Then you have first order, second order, third order maximum. Okay, with the slits 0.2 mm apart, so that is a small d, and the screen 1 meter, that is a big D. The third bright fringe from the central bright fringe is found to be 9.49 mm from the center of the screen. So that is a y3, because this is the third order bright fringe. So your n equals to 3. What is the wavelength of the light? And how far would the slits have to be so that the fourth minimum, which is the dark fringe, will appear at 9.49. Okay, so for the first one, part A, you have the small d, you have the big D, you have the y3, and you know n equals to 3. So from there, you can use the slit separation equation to find the wavelength. For the second one, part B, how far apart would the slits have to be if now the position at 9.49 right here is a fourth order maximum. So where is the fourth order maximum on the screen? Let's take a look. In between the zero order and the first order maximum, I have the first dark fringe. So this is the first order dark fringe. Second order, third order. The fourth order is actually above the third order maximum. Okay, so that means now I want it to be lower down. That is, the split separation must increase because now the fringes are closer together. Remember the inverse relationship? So when the split separation increase, then the fringes will be closer. Okay, so like what I mentioned just now, all this is given. So I just need to recall the equation, or you can straight away use y3 equals to 3 lambda small. Or you can write down the general equation first. Yn equals to n lambda big D over small d. Substitute in, so you get an answer of about 633 nanometer. That corresponds to red line. Okay, in part B, right, dark fringe is found in the middle of two successive bright fringes. So the distance between successive bright and dark fringe will be 0.5 delta 1. So that means if I were to count from the third maximum to the fourth minimum, that is a 0.5 delta 1. I'm going to let y prime be the new fringe separation, and d prime be the new slit separation. Okay, so you're given the question at 9.49. This is the position where you have the fourth dark fringe. So y3 prime, that is the distance from the central bright fringe to the third order bright fringe, plus another 0.5 of delta y. Delta y is the distance between successive bright fringes, so plus half of that. That will give me the position of the fourth order bright fringe. Okay, I discussed in the lecture notes during the lecture that we can also use n equals to 3.5 for the general formula that we have of fringe separation. So if you use n equals to 3.5, you end up with the third step. So you start straight away with the third step. You have 3.5, which is 7 over 2 lambda big D over small d to be equals to 9.49 mm. So from there you get your d prime, which is bigger, 2.33 times 10 to the power minus 4 meters. Okay, now we come to the last part, which is the single and multiple slit diffraction. You can find that on page 21. We already watched this video in the lecture, so I'm not going to play it again. But I have put the link in the region where you can find in the Google formula where you can find all the recorded lectures. Okay, so if you're interested to watch, you just click on the link. The video on the single slit diffraction is only relevant in the first 4 minutes. After that, there is a derivation on how the single slit formula is obtained. Okay, so that one is not in our syllabus, but I will encourage you to take a look at it. Then one thing to note is that the width of the slits, right, in the A-level syllabus is mentioned as the symbol A. Here they use W. Okay, so in my lecture notes, I use A instead of W. I also mentioned in the lecture that there is a small mistake in the lecture in the video, that is before spreading, right, notice the width of the distance between the wavefront, that is your wavelength. It should stay the same after spreading, but in the video, right, after spreading, the wavefront are closer together, so that is the minor mistake that you need to be careful. Okay, so for a single slit, as mentioned in the video, although there's one slit, the wave itself is already spreading. So that is why you are able to see the interference pattern, or usually we call it diffraction pattern, but they are the same thing. Okay, so usually we will say the pattern formed by a single slit is called diffraction pattern. But for double slit or multiple slits, anything more than one slits, right, the pattern we call interference pattern. But some textbooks actually use it interchangeably. That means for a single slit, sometimes they also call it interference pattern. Okay, so whether it's diffraction pattern or interference pattern, they actually mean the same thing. That is what you see on the screen, the bright dark region. So a single slit, the wave pass through, it is already spreading, and then I have a pattern here. Notice that the width of the central bright fringe, right, is very well spread. It is spread quite a bit. So this is as a result of the diffraction. I let the width of this zero order bright fringe be W. Okay. And then this angle theta is the angle between the straight through position and the first order minimum. Okay, in single slit, we are interested in the position of the minimum because sometimes you might not be able to see the first maximum. Okay. So derive the formula when you have a minimum. So this equation here, which is the single slit equation, if you watch the video, they actually show you how this equation is derived. This is based on minimum. So the A sine theta, theta is the angle between the straight through and the minimum, will be equals to n lambda. N is the order of the minimum. So if I'm referring to the first order, your n will be equals to 1. And if I make sine theta the subject, I'll have lambda over A. If the angle is very small, then sine theta approximately to theta, so I'll have this angular position here, where the first minimum occur at lambda over A. Similarly, if you are lucky, you might be able to see a second minimum. It occurs when n equals to 2, so that is 2 lambda over A. And so that is the position here. So on the screen, right, the spots that you see, they appear at different positions because of the different theta from the straight through position. So your theta 2 will be here, your theta 1 will be here. Okay, so that is the single slit equation. I mentioned just now, A is the width of the slit. The big D is the same. The big D is still the distance from the slit to the screen, same as a young double slit experiment, the same symbol. And we also need this condition whereby the distance from the slit to the screen have to be much larger than the width of the slit in order for the light rays to be almost parallel and the angle to be small. Okay, I want you to focus on this triangle here. And there's one thing that we are always interested to find, that is W. W is the width of the central bright fringe. So how to find W? This is the angle theta, which is the same as this angle theta here in your single slit equation. So theta will be equals to opposite, which is half the width, so it's W over 2 over big D. Okay, so with this formula, if you know the angle and you know the big D, you'll be able to find the width of the slit. Okay, then the next section, which you can find on lecture notes on 2.2, this is a result of page 23, section 5.2. This resolution of a single slit is an application or a result of a single slit. So in this video that you have watched in the lecture, again the link can be found in the Google form for the recorded lectures. So for this video, right, he's trying to explain to you when is it that you can tell two objects apart. Say you have two objects that are very far apart, like those two here, they're very far apart. You can still see that there are two objects if, when they pass through a slit, we all have a natural slit of two actually, the pupils. When we see an object, the light actually enter our eye through the pupil and then form the image on our head, which is the screen. So if you have, say you're looking at two stars that are very far apart. So star 1, the green star, will actually send the light, pass through the pupil of your eye, say the slit, and form a diffraction pattern. Similarly, the second star will also pass through the slit, the pupil of your eyes, and form a diffraction pattern. If the two diffraction patterns are far apart, no overlapping, you can tell the two objects very easily apart. But when the two objects are closer together like this, and the interference pattern or the diffraction pattern start to overlap, okay, this is when it is just resolved. The condition is the maximum of one pattern must fall within the first minimum of the other pattern. Similarly, the other side also, okay, the other pattern maximum fall within the first minimum of the other pattern. Okay, so we have the green and the maybe pink pattern. So you can see that the peak of the green diffraction pattern fall into the first minimum of the pink pattern. Then the peak of the pink pattern fall into the first minimum of the green pattern. So when this happens, that is a time whereby you can tell the two objects barely apart. This is the smallest distance that the two objects can be, such that your eye or whatever the slit can still resolve, that means tell the two objects apart. The angle between the two light waves, right, will be the minimum angle, the smallest angle possible. Anything smaller than that, you're not able to tell the two objects apart. Or on the screen, you will just see them as one object. This is the case whereby the two objects are closer than the middle one, whereby the theta, right, if you were to draw a line, is even smaller than the theta minimum. So for this, you can see that the diffraction pattern overlap completely, and you see them. This is the screen. You will see that it's just one object. So this condition whereby the two objects are just resolved is called the Rayleigh's criteria. Okay, so I'm going to illustrate again. Let's suppose I have two stars, S1 and S2. S2, the light will pass through the slit, form a diffraction pattern, which is red in color, if the star is red, and send out red light. S1 send out blue light, so it will form another diffraction pattern like this. So using the principle of superposition, they are going to overlap. And the color that we see, surprisingly, is not red, not blue, but it's going to be purple, because they superimpose. And as a result, on the screen, what you will see is that there are still two peaks, because the maximum of the blue pattern fall onto the minimum of the red pattern. Similarly on the other side. So this is when it is just resolved. So on the screen you see something like this. But this color is supposed to be purplish. So you will still see that there are two objects, two stars. This is what we call Rayleigh's criteria. And this angle is the minimum angle. So this is the condition for Rayleigh's criteria. According to Rayleigh, for two objects to be resolved, okay, the central maximum of one pattern falls on the first minimum of the other pattern or other image. Then from the wave theory, we know that A sine theta equals to lambda. Using small angle approximation, sine theta approximately equals to theta. Therefore, to find the smallest angle, theta minimum, we call it the limiting angle of resolution. That is the minimum angle for two objects to be just resolved. It will be equals to lambda over A. This is from the wave equation. Okay, you have A sine theta equals to lambda. Bring the A over, so you have sine theta equals to lambda A. Okay, angle is going to be very small, so we're using small angle approximation. Theta minimum will be lambda over A. Okay, let's take a look at the multiple slits of grating. It has thousands of slits here. Okay, not just one, not two, but thousands of slits. This is a section of the grating, how it would look like. You can see that there are some slits here, but this is definitely not the full grating, just part of it. The distance between the successive two slits must be constant. We call it the small d, just like in the Young double slit. Okay, so each of these slits will send a wave, light wave, and it will hit on the screen. Okay, they will all hit at the same point on the screen, because remember the distance from the slit to the screen is big. So all these ray will come almost parallel. and they are all at angle theta. Okay, so I have a laser beam. When it passes through the grating, it will start to spread and it will form interference pattern on the screen. So this is the central order maximum, then your first order, second order, just like what you see on the young double slits. But if you take a look at the pattern for the young double slits, which is in your lecture notes on page 18, the difference here is that for the young double slit, the bright fringe, there is a spread. Okay, it's not so sharp at one position, but there is a spread. But for grating, there is a spread. It's very sharp and focused at one position. The reason is because you have thousands of slits. So you have thousand light waves reaching at this point to give you constructive interference. So the intensity is definitely higher and the position is very precise. Because once you're slightly out, say slightly below the bright fringe, right, it's going to be a dark region because you will be able to find a wave that actually cancels with this wave. So at every two waves that come to the dark fringe, they will have destructive interference. So the thousand slits, right, the 10,000 waves, you can pair them up such that all these points here, they are all destructive interference. So that is the result that we see. If you use a white light source, instead of seeing one line, you see a spectrum. Because white light consists of 7 colors. So for the first order maximum, instead of one spot here, you see many colors actually because of the spectrum. So all these are first order. Then you have the dark region, followed by that you have the second order spectrum. Violet light have the lowest wavelength, so it will have the smallest theta. Red light have the longest wavelength, so it will have the largest theta. The formula is the same as the double slit. So we're going to look at the double slits again. We call this diagram. Then we consider this triangle. We say that the path difference that is S to A must be n lambda because at the point P you have a constructive interference. So for a grating, the same discussion can also be used, but instead of just one pair, we have many pairs. So your sine theta, right, which is this triangle, will be opposite n lambda over d. So for double slit, we move on to find yn. But for grating, we just stop here. We are not interested in the distance between the fringes, but we are interested in how the angle theta, right, is related to the wavelength. Theta is the same as before. So this equation typically comes from the young double slit. Okay, with that, we take a look at example 6. You have a beam of white light incident upon diffraction grating after passing through a filter that allows only wavelengths between 400 nano and 600 nano to pass through. Okay, so we have the two ends of the wavelength from the smallest 400 nano to the largest 600 nano. The angle between the red and the blue ends of the second order spectrum is 60 degrees. So that means they're telling you between the red and the blue, the start of the second order spectrum and the end of the order spectrum is 16. So how many lines per mm are there in the grating? The blue color would correspond to the 400 nano, then the 600 nano correspond to the red. All the other colors are filtered off because there's a filter here. So by the way, when I say all the other colors, that is before this 400 and after this 600. Okay, so this is what we have. In between, we might have other colors, but it's not of our focus. We are only interested at the two ends, which is where the 400 nano is and the 600 nano is. It will be good to draw a diagram. In this diagram here, Okay, show what the question state. This is a second order spectrum, so there should be another one below, okay, red and another violet, so that you should see another spread of light here. Correspond to n equals to 1, it should be lower. Then this is a second order, so it is higher, the theta is larger. Then recall for weighting, we have d sine theta equals to n lambda, so we can form equation. Okay, but this angle theta, right, is defined as the angle from the straight through position. So this 16 degrees is not the angle theta. So I will start with introducing the angle alpha, which is the angle from the straight through position to the second order blue light. If you say blue light, but I use a purple. Okay, never mind. 400 nano. So I have d sine alpha to be equals to 2 lambda. So this is my first equation. Second equation, the angle for the red light will be alpha plus 16. So d sine alpha plus 16 will be 2 lambda. Two equations, two unknown, namely your d and your alpha. So you solve equation 1 and 2. Your alpha should be 27.1 and your d is 1.76 micrometer. So with that, right, you can find the number of lines per mm. Just take the reciprocal of d. So it's about 5.7 times 10 to the power minus 5 meters. Example 7, this is a continuation from example 6. So you are told that in the previous example, you're asked which wavelength in the fourth order spectrum will overlap with the green color light of wavelength 550 nano in the third order spectrum. If they overlap, okay, overlap on the screen, that means they must have the same theta. That means the theta 4 that correspond to the wavelength of fourth order spectrum must be equals to the theta 3 that is the green light in the third order spectrum. Okay, so this is something that you need to know. Overlap means same angle. So theta 4 equals to theta 3. That means sine theta 4 equals to sine theta 3. And sine theta is n lambda over d. So for fourth order, n equals to 4. For the third order, n equals to 3. You are given the wavelength of the green light, 550 nano. So you can substitute in. You can leave your answer inside of nano. So wavelength is about 413 nanometer. So with that, we come to an end. Okay, if you watch this lecture before 26 November, please remember to do it.